Okay, today's going to be a short session for two reasons. One is I'm not well prepared. Two, we started late.
I take responsibility for the second.
I'm just going to give some ground rules for this session. It's going to be happening once a week at least. It's going to be an hour or an hour and a half, depending on how long we last. The purpose is to build our knowledge in finite fields, and then we can get into more complex things eventually. Okay. Whatever. I mean, everyone's expected to basically just review it offline, just to keep right. I mean, I think at some point it's going to it's going to get difficult to stay in this forum, and like unless you're here every time, like missing is going to be a problem.
It's recorded, so we can...
It's recorded, fine. No, so that's a tool to make it up, right?
But it would
I'm not necessarily taking it upon myself to do all the lectures. I'm just kicking it off. We'll split it up. We should try and the important thing is it's good, you know, that we'll have a discussion here and we can ask questions, and no one's expected to know everything, and we can take things if we don't know. Like if you ask me a question and I don't know, we can take it offline and then maybe talk about it next session. But let's try to keep on track. Okay, so try to stay within the topic, right? We don't want to take it. So if I see that people start to ask questions off the topic, I'll say, like, it's not for this session, all right?
Also, since it's going to be published on a public platform, we should keep it like general and
right,
not specific
right
to our use cases.
Right. Okay. Now, this is lecture notes. I'm just going to give you, I'll write just keywords so that you can find it and print it for yourselves or look at it after. We're not necessarily going to be following these.
Why
one
will
sec.
it be published? What was that about?
For educational marketing, I don't know.
Whatever.
I
Let's
think
see.
It was supposed to be private. I mean,
Listen. Right now.
Not necessarily.
There was an idea to record it, so we're recording it now. Okay. We're not publishing anything yet. Okay. My notes that I've been looking at, they're called finite fields. Okay, and they're by it's actually course notes. Sophie, this is hard to pronounce, so I'll write it. So I don't know how to pronounce it, so I'm not going to even try. Okay. I'm sure if you search this, you'll find these notes, okay? And it's from 2012, 2013. There may be other formats of this. Okay. Today's topic is groups. I imagine that we're going to continue talking about groups the next session too. Okay, we're going to try to, I mean, we're not going to take like, like we're going to stick to simple examples, right? Like groups of numbers and things like that, maybe matrices. We'll try to not get too, what's the word?
Abstraction?
Yeah. We'll try to not be too abstract, right? To keep it at like a ground level.
So like during my PhD, this is what all the great mathematicians who are there would say, like you every mathematician talks abstract, but he understands it through one example. So that's what I also want to try to do. At least
we can
one
try
solid example.
Yeah. So if I don't have enough examples, we can try and bring up other examples, and feel free to also come and like participating. Okay, so a group is first of all defined as a set G and one operation, and we'll just call that operation plus. Okay, this is just an abstract name for an operation. The operation is binary. Okay, so it takes two arguments and it outputs one. In order for this set with the operation to be a group, we need four axioms or properties. Okay, the first one is closure. Okay, so closure means that if we have A, B belong to G, then A plus B must belong to G. Okay, for any AB. Okay. The second one is associative. Okay, I by the way remember like the first letter of all of these. So it's CAII. Chi. You can make it CIA, but then you need another I. I don't know. Associative, right, means that if we have A plus B plus C, okay, so we can actually calculate A plus B and then add C, but we can also do it the other way and calculate these first. And so the order of the calculation doesn't matter. The next one is identity. Okay, so we've got an identity element. Usually for an additive group it's called 0, and we say that, or maybe let's call it E.
Yeah, E.
All right, so identity means that A plus E equals A, right, for any A in G. Okay. The last one is inverse. So inverse is that for any A in G, right? That's how you do it, right? There exists. Right? A to the minus 1 that belongs to G. Okay? And we assume, right, that A plus, or you know what, maybe we're not going to write it like that,
Yeah.
right? Sorry.
Confusing.
Yeah, no, you're right, because we're using the
I
plus.
think it's for
We
multiplication.
do minus A, and right, and then this means that A plus minus A equals the identity, which we call E. Okay? All right. Now, I think you'll notice, by the way, it's not relevant for now, but it will be relevant a little bit later when we get to rings, that inverse and identity are not the same thing. Sometimes it's confusing. They're not the same property. In order to have an inverse, you need an identity, but in order to have an identity, you don't actually need an inverse. Okay, and you can look at why that is, right?
Can you define the group as one operation plus, and
Yeah.
if you added one again, we added the minus.
No,
No, it just
minus is just means the inverse of. Okay, you know what? To make it easier, just
call it B.
let's no. Let's call it a not.
Yeah.
Okay.
Okay.
All right. So there is one property. Now this defines a group. This is a basic group. There's one property that we can add, okay, that is not necessary, but it is an important property, and a group that obeys this property is called an abelian group. You know what this property is?
Yeah. A times B equals B times A. A
Right.
plus B equals
Right.
B plus.
So this is called commutative, okay? And this is a plus b equals b plus a. And you can change the order. If we obey this, then we call the group abelian group. By the way, wait, maybe I'll move here now. Alright, so this is an abelian group. Sometimes it's called a commutative group as well, but you'll notice in a lot of places you'll see an abelian group. That's what it means. It just means that it's a commutative group. So let's look at examples. Kati, you got a good one? A good example for a group? A group is this, right?
Yeah, like with just like an addition operation. With just addition.
Integers. Okay. Good. So integers is a group. Is it an abelian group?
Yeah, sure.
Yeah.
Yes. Okay. So that's one. Other groups? I mean, obviously.
Real.
Huh?
Real numbers. I mean float numbers.
But real numbers are also fields. So let's try and do things. I mean, these. It's true. It's true. It's also a group. I mean, we could also write real numbers, complex numbers.
Yeah.
How about
Natural mode something. Natural numbers mode something.
natural or
Natural.
natural
plus
integer?
zero.
Right.
Natural plus
Integer.
zero.
So integers mode.
No,
right.
natural plus zero.
No, but natural and
Natural and zero.
Yeah.
Yeah.
It's true. It's true, but we usually would we usually would do z like zn, okay, right? By the way, right, this is true for any n, okay. Also for n equals 0, because 0 in itself. So if we write just 0, 0 is also a group. It's even in a abelian.
Yeah, it's 7.
It's even a field. It's everything. It's the ultimate. Okay, now how about 2 by 2 matrices? There.
If you allow, yes, yeah, why not?
So let's test it.
With
So
respect to addition,
huh?
they are.
What?
With respect to addition, they are.
Yeah.
addition.
Okay.
Yeah.
So let's call it M 2 by 2. I don't know if this is the right terminology. Okay. With addition. Let's see if that's true. Okay. So and M is
You need to specify the field that.
right. Let's say that they're over Z as well. Okay. Just to make it simple. Okay. This doesn't really look.
So yeah, that's false because Z is a group, and you have several copies of Z inside a matrix.
Okay,
so.
but hang on. So closure we've got, right? Associative we've got. Identity would be, what's that identity?
The all zero
for this?
matrix.
The all zero
Yeah.
matrix. Okay, notice the all zero matrix. And inverse because I've got the minuses, like Guy said.
Yeah.
Okay, so here, right, we can say that E equals 0, 0, 0, 0, right? Okay, how about the same thing, but with matrix multiplication?
What you
Yeah,
write
this
is
is
not
not-
seen in the recording. What you write now.
No?
He's moving
And
sometimes,
now?
so it will be seen.
This is not a group
Why not?
What?
because not all matrices are invertible.
Inverted, correct. So here we need to say that it's actually, I don't know, not sure how to write it, but
choose
we need to say that the determinant, right,
Right.
of these matrices, it's complete abuse of notation, okay? The determinant
is
is
delta.
is not equal 0, okay? Once they're invertible, it's a group, okay? Now, what's the identity for this group?
I.
I, right? I of 2 by 2. Is it an abelian group?
I don't think so.
No, it's not commutative, no.
Okay, so it's not commutative. Okay? Enough example? Alright. Okay. So, just a few, I'm gonna have to erase this. Unfortunately, the whiteboard is small. But let's maybe, you know, I mean, the point is also to be able to remember somehow. So I'll put like a compressed version here. So a group we'll say is G plus with, right? We said CAII, and with another C, which is commutative, it equals abelian. Okay? This is slightly coded, but it's a good way, I think, to just remember it, okay? Because it's the kind of thing, and actually, a lot of this stuff you need to remember, like these little properties, right? This is probably the easiest one.
We're probably never going to deal with continuous groups here, right? You know.
I think that will slowly,
Yeah.
like, well, no,
Maybe
we're
not.
not going
Yeah,
to
let's
do,
not.
but, okay. Continuous maybe not, but infinite,
Yeah.
yes. Eventually we'll also go to finite. So,
Wait, what do you mean by so, no.
Like, I don't know, like if you take the group of translations, rotations in space, and so they're continuous groups. Right?
Continuous or the infinite?
No, the X is not a discrete object.
Right.
X is defined.
So, okay,
yeah. This is
Yeah, I mean.
where we go back to this.
Yeah,
Okay.
yeah, it's up.
Should we have a code word for it? You know, in the army, there's a code word called insomnia. Not insomnia. Wow. Zambia? Oh, I can't remember that. I remember it now.
For what? For what?
So it's actually after you do something called istarut,
Yeah, I remember.
right? And you actually need to lie down and just listen out, right? To hear if the enemy is still alive, right? So so one person calls out, I think it's
Hadal.
no, Zambia.
Yeah.
And then everyone,
Zambia, like.
yeah, then everyone needs to remain quiet for like 15, 20 seconds and just listen out.
From the word zombie. Become like a zombie.
I don't know why it's funny.
The zombies
We
move.
used to do it, so in officers course, like the first few months is all like learning, right? It's like this, right? So we used to have, like in our group, seven, right? We used to do it when we had enough of like a certain lesson. One person would call it out and then the discussion would just die. And then inevitably the lesson had to like
That's a very good
discontinue and we're gone a break, yeah.
Anyway, we already saw infinite groups like set and matrices.
Yeah,
So,
yeah. Okay, so so actually a group is called cyclic. Could be, by the way, a multiplicative group or an additive group. A group is called cyclic if it has the following property. So if G, so actually
has to be finite, no?
Huh?
Has to be finite, no?
No, it doesn't have to be finite to be cyclic. It's actually, the property says that, that if B belongs to G, okay, and B can be defined as, let's do it a multiplicative group, but then I'll show you also, just as an additive group, the writing is a little bit more confusing, but if you can actually define any B as a to the power j, j is like z plus, right? It's an integer. Z plus is basically n plus 0, right? So if any b can be defined as a to the power j, we call this group cyclic, and we actually say that g, we mark it like this, okay? And a is called the generator of the group, okay? And you can see that we can also do it for an additive group, right? So for an additive group, it would be, so this is like the multiplicative version. For the additive group, we would say that b equals j times a, and it's very important to note that this is not a multiplication in the group. This just signifies that I take
Addition
a few times. I add a to itself, right? It would actually probably be better to just say that it's a, or maybe sum, right, of a from whatever, like I equals 1 to j. Okay? This is maybe a better definition.
You mean for every probably.
Yeah.
Yeah. For any b,
For any.
b in G.
Yeah.
If this is true, then this is called, let's keep this up. This is called a cyclic group, okay?
Yeah, and A is the generator, right?
And cyclic, right, group with generator A.
The symbol of every is like this, not ככה. ככה.
כן.
החץ
שמעלות של
תעשה רוטייט מין קלוק מינוס
כמו
90.
A הפוכה.
Not the way that I...
מה זה הזווית ולא...
לא. לא.
No.
לכל בי. נכון.
Yeah?
Yeah.
Yeah.
Like reverse A. Yeah. Like
Yeah.
upside down A.
Yeah.
בטח, זה נכון, זה בלוגיקה.
For all?
For all, yeah. For all B. Yeah, it's reverse like flip
Yeah,
A.
yeah.
Like, yeah, flip A.
I've never done it like that and never seen it. Oh, we'll argue about it
So
after.
this is a notation for angle.
אנגל.
אנגל,
Yeah.
yeah.
Okay.
This is for maybe for second grade. We use this angle. All right.
Oh, optics.
Never mind. Okay. So let's look
Just
again
a
at
question.
examples.
Without-
Wait, what's the time?
How can
Oh, okay. So we still got 15 minutes. Yes.
an infinite group be cyclical?
Because that's the definition of cyclical.
Okay.
It just needs to be consistent. That's all. Okay. It's also considered a cyclical group. Obviously, if it's finite, then and Kartik will show you how you take something finite and actually, right? What's it called then? In
Blowing.
synergy,
סרנג.
when you take like the unit circle and you put it on the infinite line.
Stereographic projection.
Right. And then
Yeah.
the cyclic property
It's a
remains.
very good example.
Yeah. Okay, guys. Okay. Examples. Okay. So again, Z, right? Is a cyclical group. What's the generator of Z? Okay. Or
One with plus.
huh?
One with plus.
With plus.
One
yeah.
with-
Plus will also
Plus, yeah.
Right. Sorry. This is what I meant.
Yeah, because it's not a group with respect to multiplication.
So when they
What about
What?
one
they-
with minus?
When they write notation, it's
Huh?
like angle 1 with
One
an
or
operation
minus.
also indicated. That's the notation.
Oh, just a sec.
When
Yeah.
they write, I'm just asking because I don't remember the notation. You always write with the operation also in it, like.
That's not the operation. That's just to
Just it means.
say that it's not a minus one. Yeah.
Yeah, so also minus 1.
Yeah.
Yeah.
So minus one is also a generator, right? So this is equivalent to that, and it's equivalent to that.
Yeah.
Okay. Notice this is okay because actually maybe we need to do it.
Wait, how do you get from 1? How do you generate minus 1 from 1?
You multiply it by j equals minus one.
Yeah, but multiplication is not.
It's not a
with respect to
multiplication. No. We said that it's like you do something like this, but like a
So
negative sum.
how many ones I need to add to get minus 1? Because I think.
Yeah, I think that's a problem.
I think I think it needs to be only the positive one.
Positive or negative?
Positive one. Negative.
No? So,
No.
So how
No.
do
This essentially multiplication by j is.
Yeah, maybe.
I don't.
Addition.
But I don't have the notion of minus.
No.
Okay, maybe.
Let's do. You know what? Let's do something else.
Maybe let's just do something like roots of unity.
Yeah. Okay. I think it's more about terminology.
Yeah.
But let's look. I mean, we looked at z, at the group z, at the set z with plus.
Right.
No, it
Yeah,
has to be
double.
with plus.
Yeah.
Yeah. No, but
It's
I think that minus one is fine. Like I think it's
No,
it's
but-
within the rules.
It's not.
But minus
Okay, but
1
like two isn't, right?
But with minus
Because-
1 you can't get to plus 2.
yeah, you can get to
Huh?
positive.
Yeah.
So with minus 1 you
can only
can't get
get
plus
the
2.
Negative.
Negative numbers.
Yeah, you
Yeah.
generate only the negative numbers, you don't generate the positives.
Yeah, it works
Maybe at
only with
infinity
the z.
So we need to think about to extend this rule, but it's meant to be fine.
Maybe because it's infinite.
No, because you can do.
Because the loop is
No, no.
I don't really fully understand.
Maybe the definition of the
The
addition.
definition here is
It's for finite groups.
okay, because you can do like if you have a generator, say minus one,
Right.
okay, like you can get to one with the addition, just with the inverse of the addition, and the inverse is in the group. It's fine.
Like
Ah,
J
okay.
is negative or.
Yeah. So it's really maybe
But the inverse one.
maybe
is
this
the group.
definition is not
Yeah.
exact. Okay, but if inverse is in, then you're
Yeah.
supposed to be able to generate it with minus
Yeah.
one.
Okay.
Yeah.
Does anyone have any other example?
Roots of unity.
Huh?
Roots of unity.
Roots of unity.
1 omega omega square. Cube root of.
Right, but that's like taking, say, the group 2, right?
Yeah.
I mean, we don't actually need to go to roots of unity.
Yeah.
And that would be all the group of all even numbers, right?
Hmm.
Which is valid. Okay?
Yes. There's also a integer modulo prime number.
Yeah.
Right. Right.
Oh.
But we're gonna get to a lot of that, so with that, and by the way, there's integer modulo, not a prime number, it's also an additive group. By the way,
Cyclic group, you mean?
Yeah.
yeah, now is, how about, by the way, just a question, since we're on it, right? Maybe a lead up. So, if I take all the odd numbers, right?
Yeah.
Are they a group?
Yeah.
Yes.
Are odd numbers a group?
No.
No, because it's not.
They don't have zero.
No.
So first of all, so
It's not
what if I
closed.
add zero?
It's not closed.
No, it's not closed.
It's not closed.
It's not a closed.
Right,
It's
so
not
that's
closed.
no closure, okay?
Sure.
Okay. And it's certainly not cyclic if it's not a group. Okay. So, let's move on to the next topic, right?
Actually, when we do point doubling, essentially, this is.
What?
Okay.
No spoilers.
Cyclic is another property.
Yeah.
Like,
Yeah.
a group is not necessarily cyclic.
Group doesn't have to be cyclic.
Okay.
But yeah, but it's yeah. But I guess if it's cyclic, then you can use that property for certain things. Okay, so now we're gonna leave this. That's the first topic. Now we're gonna talk about something called an equivalence relation. Okay, and an equivalence relation is actually something. We're taking a step back. We're going back to sets. Okay. For equivalence relation, we don't actually need the operation, okay? And we'll define it like that. So we've got a set S, okay? And then we've got a subset R that belongs to S cross S, okay? This just means that it's a pair. Okay, by the way, the subset R is considered a subset of S as well, okay? That's just from a terminology perspective.
How could that be considered? Because it's
It's just the terminology that you'll see.
okay.
Like you'll see that if I look even at the like set of all pairs, it's also considered a subset for some reason. Okay? Yeah, it's a bit confusing, but
Yeah, just what's
actually-
the cross
Right.
notation? What's the cross?
The cross notation basically means that this actually means that I've got
Yeah, it's like
A, B. Okay, it's a two-element pair,
Okay.
right?
This is what
Such that
okay, it's a standard notation inside.
A and B belong to S.
And actually,
Like this I'm more familiar with.
Okay.
Yeah.
Actually, that notation is incorrect.
What?
The belongs to, it needs to be
It's
just.
a just a subset is like this.
You're right.
The-
You're right. You're right.
But you define R as the
Huh?
entire S process, right?
No, it's a subset.
R is a subset of S process?
Yeah, because we're going to now. R is just some subset.
Yeah.
Okay.
Mm.
It's some subset. Now we're going to define how we find R. Okay. So we're going to say that that R is actually an equivalence relation if it obeys three properties. Okay, again. Okay. But these properties, I think that maybe they're not super important to have at the back of your mind always for our purposes. Okay? At some point we're gonna get past this, and so it needs to obey a property called reflexive. Is that spelled? Yeah. Reflexive. Reflexive basically means that SS is in R. Okay. So all the pairs of like the same elements, right, is in R. Symmetric, which you could probably guess. Symmetric means that if ST is in R, then also that leads to TS in R. Okay, I'm skipping the in R.
Yeah.
And then the last one is called transitive. Transitive means that if ST and TU is in R, then SU is in R. Okay. Now, it turns out these are called equivalence relations. EQ, it turns that an equivalence relation creates a partition on S, not on S cross S. Now we'll show it through an example. Huh?
Is it also the other way around? If SU, if I take,
Yeah, you
Like
can
always
change.
partition
You can
it in
change
any way,
these two,
right?
of course, because ST and U are any elements, right? So they all belong to, like all of these elements are any elements in S, essentially. Okay.
Yeah, but it doesn't follow the other way.
Yeah.
It's not obvious.
Maybe you want to have a T.
No.
Ah.
What did you ask?
No, I wanted to know if I
No,
if I
he
have a
said-
set that is reflexive and symmetric, can I say that it is also transitive? Because I can
Yeah, of
see
course.
it.
Look. Okay. So let's change these two, right? This is just an example, right? So if we have ST and SU. So we're asking now if TU is in, right? Because you're saying maybe it's not, but then all you need to do is go to the symmetric property, right? Because if SU is in, then that means that also US
yes.
is in, right?
Right.
And
that's
so on.
the question.
Right.
Right?
Yeah.
Okay.
So
And
transitive
you can
is
use
like
it
a-
for the homework. Or the proof,
So transitive actually follows from a reflective and symmetric, right? That's what I wanted to ask. Is that a correct statement?
Ah,
or
no,
it's a-
No, otherwise.
No, you have to have it.
No.
You have to have a.
Yeah. This
Yeah.
is not no, otherwise.
I
Um,
can
Part
show-
of the definition.
Yeah.
Can we find an example? Yeah, just think that transitive means that you've got these trios,
Right.
right?
Maybe
So-
greater or equal them. You have reflexive and transitive, but not symmetric.
Right.
Okay. Because each number is greater or equal than itself. If S is bigger than T,
Right.
and T is bigger than U, then S is bigger than U. But if S is bigger than T, it doesn't mean that T is bigger than S.
Right.
So you have reflexive and transitive, but not symmetric.
Right.
Okay.
Right. You're using an example of like
Greater than equal.
greater.
Greater than.
Yeah.
Right.
Makes sense.
That's the relation. Okay.
Yeah.
So maybe we continue with an example before we or maybe we'll define an equivalence class which is related to this, which is actually the point, but we'll do it through an example, okay? So let's take, and this is not in the notes, let's take a group S which equals A, B, and C, okay? And let's now create an equivalence relation, okay? So I'll say that AA is in, BB is in, whoops, and C is in, right? Right, so just because that's what I decided, right? So that's fine. Now,
This is fine.
by the way, this is fine, right?
Yeah.
But let's do it a little bit more interesting and add also maybe BC. Okay? So if I add BC,
C,
I
obviously.
now need to have what?
CV.
CD.
CB, yeah.
Right.
Yeah, that's all.
But that's fine, right?
That's it, yeah.
Okay. So if I stop here, then now I'm going to define the equivalence class based on this. Okay? Now the equivalence class, the proper definition, I'll put it here and then we'll do it, we'll do it on the example.
If you take the AA and BB, right?
Let's do it again. Again?
No, it's good.
So if we look at equivalence class, okay?
Yeah.
So equivalence class actually says, we mark it with square brackets, okay? And it's actually equal, the equivalence class is equal to all T that belongs to S. Note that the equivalence class is not pairs. Okay, it's actually like a subset of S. Okay, such that ST belongs to R. Okay, so it actually, you can see that the equivalence class is actually all the pairs that are generated from S. Okay, so S is sort of like a generator of the equivalence class according to a given relation. Okay?
What's the, you have T belong to S? What did
This
S,
is big S and this is small s.
yeah.
Okay.
What did the little S stand for?
The little s is the little s is basically any s in little s comes from S. Right? Everything comes from S.
The equation
But
plus are
you
not
basically
unique.
choose one S and then you can generate an equivalence class within R.
It's not a unique.
What?
It's not
What's
unique.
not unique?
The equation classes. There should be more than one S.
Yeah,
Several
you
sets
can. You can do an equivalence class for any
So every
any element in S.
Right.
Okay, but notice that, for example, if right, if say we've got an equivalence class.
No, but I mean that you can separate S to equivalent class. Let's say maybe A is equivalent.
We'll do it
class,
in a
second.
and maybe C or B and C would be another.
Exactly.
equivalent
So
class.
Right,
This
exactly,
one-
and we're gonna see that exactly on a simple example.
So this definition is with respect to a specific R, right? Specific partition.
Yeah, it's
Sure.
a specific relation. Yeah, sure. Yeah.
Yeah. And so
You see, like here, it would make a difference if we changed R.
Yeah.
You'd get different
so
equivalence
isn't
classes.
it an S of R or
No. S is in S. R is pairs. Right?
okay? Because there are a lot of equivalent classes, each one
That are equivalent to one
Yeah.
another, right?
and some
So, like,
that
if-
means
here,
you
if-
add up the-
Just a second. If ST belongs to R, right?
Yeah.
Then what can we say about these two equivalent classes?
but yeah, equivalent.
They're equivalent.
both.
They're
With-
equal,
with-
right?
Yeah. With relation
Okay.
to R, yeah.
It's always with relation to R.
Yeah.
Okay, an equivalence class goes according to a certain equivalence relation.
If
Yeah,
ST
I mean
belongs
like
to R,
the equal sign.
I don't think.
Yeah, but that's
Yeah.
implicitly assumed.
Yeah.
Wait, but that what you wrote, I don't think is correct.
Why not?
Because T can go with all other stuff that S doesn't go with. And S
But can it?
Has to be symmetric, no?
You need to go back to this and you'll see that actually S will generate everything.
Yeah, okay.
Yeah.
Yeah.
It's not obvious to me, but it's
It's more-
Because of that.
Is it more-
That and that will lead to
that and that. But if you have SU,
Yeah, but how would
So maybe this
Notice- notice that once you have S, because ST is part of it, right, it brings T. Once you have T, T will
Then
pair
T
up
will-
with everything else
wait. S.
because of that.
we can try this with an
But
example.
S is
maybe.
all the T that belongs to S.
Hmm? Which? This?
And the definition.
Ah, you mean if ST, you mean all the T's?
No.
The definition is
These
quite
are two.
confusing.
This is one very specific pair. Okay?
It's
But if SU belongs to R and TU doesn't belong to R.
But if SU belongs to R, okay, and ST belongs to R, then TU, that's
ST,
transitive. right?
S it's all the
Because of the transitive, yeah.
S it's all the dots S, that for some T in S,
Okay?
make that relation. S and T
Yeah.
make
No, this solves because of the transitiveness. Yeah.
Mm-hmm. Yeah. Now, let's look at this, and Ellie actually did a bit of a spoiler before, right? So let's look at the equivalence classes, right? Let's see what happens with, right, A. Right, so A, what's in A?
A.
Just A. Right? And you can look here. Right? No one pairs up with A, just itself. What about B?
B and C.
B and C.
B and C. What about C?
Same.
Same. If we take now, like the unique, the unique classes here, right, which would actually define a new set, right? It would be the set of A and the set of BC. This is what's called a partition, okay? And an equivalence relation, because of these three properties, the equivalence classes of an equivalence relation, okay, all the classes, obviously, will always define a partition on S, okay? And that's the key property.
Yeah, because it means that you will never have the same element in two of the partitions of the
Yeah.
classes.
Exactly.
Right. An element can't be in two classes. Because if it was in two classes, then it needs to transmit itself, and then it would become the same class, right? It will unite the class into one class. That's exactly what we said before.
Yeah, total additivity.
Okay.
Okay, what's the time looking like?
So,
Oh,
just to
Okay.
summarize, a partition of a set is the set of equivalence classes.
the what?
How do you phrase
Again,
it? The partition of any set
Yeah.
is the set of equivalence classes.
Or maybe the other way.
Oh,
The equivalence
class.
all the equivalence classes actually
Partition.
they partition the set. Okay. Okay. I think maybe we should stop here. Maybe no. We're not going to stop here. We're just going to do one more thing that I think is important, because if we're already touching equivalence classes and equivalence relations, okay. At the end, what we're mostly interested in are the equivalent classes, okay. Let's see. So we had equivalent classes, and which leads to equivalence relation, which leads to equivalence classes. And now we're going to take, it's sort of like, it's not an example, right? It's maybe more than an example, but if we take the following, we take, say, any integers a, b that belong to z, okay, any two integers, and n that belongs to n, right? So it's a positive integer, not zero. So we can say it in a few ways. Okay, we can say that A is congruent to B modulo n, right? And we write it A equals B mod n. Okay. Right. So A and B are equal modulo n. right? And this is equivalent to saying that A minus B, that basically n divides A minus B. Okay, obviously, like so that. And it's also equivalent to saying that A equals B plus K times N, where K is, right, K would also be from here, right? With K in B, right? Yeah, these are all like equivalent ways of saying the same thing. So now we want to check whether this congruence is an equivalence relation. Okay? So let's check it.
Yeah.
Ready?
Yeah.
Okay. So first property is we need.
What are the groups again?
This is
Equivalence
we want to define. We basically are looking
What S
at
and R?
we're looking at pairs A B
Such that. yeah.
such that whatever.
Okay. And
Okay, and A and B we said that they're from Z.
R
So
is
first,
This is R.
no R is Z.
Reflexive.
R is Z on Z.
Z cross Z.
Yeah, yeah, yeah.
Reflexive is obvious.
R equals or
yeah.
R belongs, right, to Z squared, you could even write.
Okay.
Or Z by Z.
Okay.
Okay, so let's check if it's so reflexive.
Yeah.
Reflexive
Right.
is obvious.
AA,
Right.
Yeah.
easy, right? AB,
And
BA, that's symmetric.
Yeah.
Mm-hmm.
Right?
Yes.
We can exchange those two, right?
Yeah.
What about transitive?
Yeah. Yeah.
How?
I think so.
Yes.
So let's say,
Yes,
right, we
yes.
say that, let's erase this, let's do it, right? We say that A equals B mod N, and then we've got, say, B equals C mod N, and then we ask the question, is A equals C, right, this is a question, mod N,
Yeah.
right?
Yes.
So yes.
Right? Because essentially, right, all it says is that the difference between any of these, any pair within the three is a multiple of K or is can be divided by K.
Just put the B, so A equals.
You can
Right, no,
substitute
we can substitute, but I
Yeah.
think it's even easier than that because you can just say that if you look at any difference of any pair, it n divides any of these differences, right?
It's called. It's a residue class. What's the name
Huh?
of this specific? It's residue.
This
class?
is an equivalence relation.
No.
No, no,
But
no.
the specific.
Residue
example.
is something else. That's when we get to rings. This is equivalence. Okay?
Okay.
Right. Now, all right. So now let's look, for example, at A, okay, at an equivalence class, okay? An equivalence class using this relation, or maybe instead of A, let's write alpha just so that it's not confusing, okay? Right, so alpha would be equal, right? Be equal what? We haven't used T, okay? So T in what? Z, right? Right? Such that, and now we can take any of these conditions above, right? And just say that
Alpha.
like T equals alpha mod N, for example. Okay? Alright. So So this would be an equivalence class,
Oh, yeah.
right?
So, yeah. So it's obvious that they make a partition.
Let's look at that partition. So let's now take an example. We'll change the. Sorry. We'll go back to blue. Let's do it up here. Okay. Second example. N equals is. Choose a small number.
5.
It's the smallest one you could. All right. N equals 5. In the notes it's 4. Okay. So, right, how many equivalence classes do you have for this?
5. 1, 2, 3.
So 0. What's the equivalence class for 0? What I mean, obviously you have 0, right?
0, 5, 10.
Minus 5, right?
Minus 5.
Okay. What would 1 be?
1, 6.
0, 1, 6.
So I could actually probably write 1 in a simpler form and just say that it's 1 plus 0. Okay? But notice you gotta be careful with this. This is not equal to 0, or actually it is equal to 0 plus 1, but for different reasons, right? But then you go back to that. But this just means that you take the set and you add 1 to each element. Okay? And it's the same when you get to 4, right? And then what's 5?
5 is 0.
0.
Exactly. Okay? So it works.
Yeah.
Okay. Now, last thing for today. This is a little bit tricky, okay? But now we can take. Right, I'm going to edit down here. I'm not going to erase anything. I'll just go on my knees. The last thing that is important is now, if we take the set 0, 1, n minus 1, and remember each one of these is a set on its own, right? Right?
Set of sets.
It's a set of sets, exactly, right? I claim that if we add the following operation, and this is a definition, okay? This is a special class. This is just a class that I'm defining. How is it defined? It's defined if we're taking two elements from here, and we add them, I define, that they're equal to the element where where we take the sum of the inside, right? And this is the normal sum. This is a special sum. This is a definition of a special sum. This is the normal sum. If we define plus for the group like this, right, and we'll say that we'll call this G, but apparently it's just a set, I claim that G plus is an abelian group. Okay? That's for you to check, think about.
Actually, I think you need to say that A plus B modular n, because otherwise it won't be in G. Because G is defined, because G is defined, it has n elements.
Where do you want to add the modulo?
In A plus B.
In here?
Yeah. Because
You just told me that 5 is equal 0.
Right,
but
you have to say that.
in G.
No.
You have n element in G.
No, hang on.
Okay.
I'm saying that take
The modulo is inherit, like one of the,
any two that you want. Makes no difference.
Okay.
The modulo is built in. That's the nice thing.
Okay.
Because that's how the equivalence class looks. It's actually all the elements. Okay.
Yeah, I think it's just a definition of thing. Maybe I'm wrong. I need to think about it.
Think
Yes,
about it.
yes.
Go over this. This is actually like a key insight that you need to swallow, and that it doesn't feel like it's
stomach
stuck.
pain. Yeah.
It needs to, you need to swallow it and then like understand it, and we'll keep going next week
Yeah.
from there.
I think this comes back again and again in various places, right? Like even when you define all your group element addition and everything, you have some
Yeah,
kind of.
we'll see that this is very strongly related to how we define isometries. But let's leave it at this. Yeah,
You claim it's abelian group for any n.
for any n.
Okay.
Sure. Yeah, check it out. I mean, we chose 5, which is prime, but we didn't need to. Could have done it with any number.
Okay. No, so any specific. This is the same n as like 5.
Yeah.
So you mean like 0, 1 to 4, like G is
Yeah.
defined. Like
It's
okay.
I think it even
Okay.
gets worse. So you could, I think that you could actually define
Yeah,
this
it's basically-
even for any
It's the same.
any number.
It's the same,
Even
right?
certainly. Wait a sec, just so that I don't say anything stupid. Can you define it for any real number? I mean, it obviously wouldn't be the same modulo. It would obey this, right? Something like this. But there's no reason that you can't do this with any real number, and it would also generate a group.
It's normal. You come back to normal modulo group, like when you define the addition like that. Like this is. This
Right.
is
I mean, you
like-
would just get basically multiples of, like integer multiples of your n.
Yeah.
And the n could be some ugly number. Could be even not rational, I think. Okay. We'll cut it out. We'll cut it out of the video
Yeah,
if we find out that it's wrong. Okay. Let's stop here and see you
Very
next
much.
time.